Our next example is a script example global persistent. I explain global variables which are visible in every workspace where they are declared as to be global, and persistent variables which retain their values and the memory locations across function calls. A local variable in a function is lost when you exit the function and does not exist anymore when you re-enter. Persistent variables retain their value across different calls of the same function, so they are not lost when you exit the function, and you find them again when you re-enter the function. Let me demonstrate this with this example script. So let's set a breakpoint at line 2 and let's start the execution. So where is okay, now we are ready to run this script. We stop at line 2. We declare A to be global. You see that global variables are displayed in a different color so that you can recognize them easily. It has now the value of 3 and it has the attribute global. Okay, then we define a local variable x, and now we call the function example global 5 times. Let's put a breakpoint at line 14 and continue. Now, when I enter this function, a is not known. It's only known after the global declaration in this function, which has its own workspace, but a is now known in this workspace, and it has the value of 3. Now we define a counter, which we use to count the number of times the function has been called. So after the declaration persistent counter, the counter is known, but it's empty. So if it's empty, then we initialize it to 1, since this is obviously the first call. So counter is now 1. Then we compute something using the input argument and the global variable, and we return the counter in the second output argument. Let's now delete this breakpoint and let's run, and this function is called 5 times and the counter returns the number of calls. If we run again, the counter retains its value, so it will now start from 5 and increase to 6 on the first call to the function. Okay, let's delete this as well and let's continue. So we have now called the function in total 10 times. And this value will persist until you change the code in the function or in the calling script. In this case, let's say we make the following change. We save the function and now the counter does not exist anymore, and we start from scratch at 1, and we have now 5 function calls since the function was changed. I do not recommend to use global variables. In general, it's much safer to pass variables by arguments. On the other hand, if you have many levels of function calls, it might be tedious to propagate one variable through several levels. So in this case, a global variable could be useful, but you have to be careful to declare it as global everywhere where you need it. So let's now pass to the next example. This is a function which contains in its file some other functions, auxiliary functions, which are not visible from the outside. So this file, example subfunctions, and this function has its own file. So this is visible. And I get its path with a which command. If I do the same for this function, geometric mean, it's not found. So this function is purely an auxiliary function to this function. And let me now try to call this function from the command window. Let's define a random vector x. Since we compute the geometric mean, all values of x have to be positive, so let me use exponential random numbers here with mean 2 and length 100. So this is a random vector of exponentially distributed random numbers, and this function then computes the mean, the arithmetic mean, the geometric mean, and the harmonic mean by using these sub-functions or local functions, which can be called only from inside this function. Okay, let's make this call. And you get the arithmetic, the geometric, and the harmonic mean. If you want to call these functions from somewhere else, you have to put them in their own separate file. In many cases, it's necessary to pass a function as an argument to another function. For instance, if you want to plot a function, if you want to find the zeros of a function, if you want to optimize a function, and so on. This is done via the concept of a function handle, and a function handle is nothing but a pointer to a function. A function handle doesn't have to point to a file with a function. It can be also defined on the fly, so to speak. Let's have a look at this example. So please open example function handle and let's run this script. So I clear all variables. I close all figure windows. And I define a function handle in this way. Its name is myFun, it's my function. Then you have the @sign, and then in brackets you have the argument or the list of arguments, and then you have the definition of this function, which in this case is a single expression. Then I open figure 1. I dock it to my window. I will do the same for a couple of other figures. So I open the figure and I dock it to the window you see in the video. You don't have to do this. This is just for creating the video. Everything needs to be in the same window. Okay, now I call the function funplot, which I've written myself. There is a function fplot in Matlab, so you don't have to do this, but I want to show you how to pass this function handle to the function funplot. So the first argument of funplot is the handle, which is a pointer to this function, to this very simple function. So when I now call funplot, you will see what happens. Let's put a breakpoint here. Okay, now the first argument is the handle, the pointer. So it's an object of class function handle. And that's its value. The value is this string. It says it has one argument, and this is the command to compute the function value as a function of this argument x. Okay, so then I go to figure 1, I clear the figure, and I continue to step through this function. And here's the plot command, which plots x in the range from x1 to x2 with the function values defined by the handle. Okay, here we have the function, the graph of the function, and we can return to the editor window and continue stepping. I use the command hold on to plot the x-axis, which is here, black dotted, and then I return from this function. The same thing can also be done with the function fplot, which is in a Matlab function predefined. So it does about the same. The range is again from -2 to 5. And the plot looks much the same as before. So let's continue stepping. I can pass this function myFun also to the function f0, which computes a 0 of the function starting from the second argument. So if I start at 5, I get a 0 at 4.2491. If I start from this 0, if I start from 1, I get this 0 close to 1, and if I start from -2, I get this 0 close to -1. You can define handles for built-in functions, for predefined functions. For instance, if you want a handle for the sine function, you can put it like this: my sine equals @sine. So the creates a handle to the function sin, which is a sine function. No need to declare the arguments, because the sine function, the function sen, has only one way of calling it, with a single argument, which can be a vector. So my sin now is a handle to the sine function, and I can call it just like the sine function itself. You can also define function handle with several variables. For instance, this handle, it has now two arguments, a and z, and the function definition is this string, this expression, a times sine of z vector times, or array times z. Now if we set a to 5 and x to a vector from 0 to 2 times pi with 21 values. I can now call this function and I get the values of this function at these points x using the value a equals 5. If you have several function handles, you can organize them in a cell array, for instance like this. So the first cell is the handle myFun, and the second cell is this handle. Now this handle has no name. This is called an anonymous function, but I can call the function handles using the cells where they sit. So myFuns of 1, this cell is this handle, so I can call it in this way. Okay, so as I said, there are also anonymous functions which have no name, which are just defined by the handle and the expression. And you can evaluate such an anonymous function by using the function feval, function evaluation. So you put the anonymous function here, and here you set the input arguments for this anonymous function. So this will give these values of the function cosine x plus e to the minus x. You can also compute a zero of this function starting at 2. This will give you 1.7461. If you start at 5, you will get a different zero. And of course, you can also plot this anonymous function using the function fplot. That's an anonymous function, and this is a range where the function should be plotted. So we go to figure 3, and now we can plot the function, the anonymous function, like any other function you have defined. Our last example is about the concept of an inline function. If you have a very simple function, you may not want to store it in a separate file. In this case, you can use an inline function, which means you have a character string which defines an operation using variables, functions, other functions. And the command or the function inline will create an object f, which is an inline function, which is, let's have a look. Let's run this script and step through line 2. Then f is class inline, and you also see the arguments that have been determined for f, and they are in alphabetical order. So the inline function finds that the arguments of this function are capital A, the amplitude. You see that this is an harmonic oscillation. The amplitude, omega, the frequency, t, the time, and phi, the phase. And these are put in alphabetical order. Now you can call this function if you define input arguments and then decode it like any other function. For instance, you set the amplitude to 2, the omega to 3, the time to 1.5, and the phase to 1. And then you can compute the value of this function, and it's minus 0.7016. It's not possible to call this function with less or more arguments. If you try to call it with only 3 arguments, of course you get an error, which I catch here. If you're not satisfied with the alphabetical order of the arguments, you can define your own custom order by just listing the arguments in the order you want them as character strings or character vectors. So if you define f like this, then you see that the arguments are now in the order you have specified here, t, a, omega, phi. Okay, now you can call f again with a different order, and you get, of course, the same value. So inline functions are useful if you have, let's say, command statements, expressions which are computed very often, but are too simple to be put in a function of its own. So in this case, I would recommend to define an inline function.